Okay, thank you, Cloud Person. Welcome back. I hope your spring break was restorative, restful, productive, all of the above. And so the purpose of today is to introduce you to some of the APIs that we'll be using when we connect these devices to the internet. Shortly, about maybe another week or two, we'll be pivoting to the Raspberry Pi, and we'll look at some of the differences between the Raspberry Pi, which is an embedded computer, and the Arduino, which is a microcontroller. And then we'll look at examples for interconnecting multiple devices with one another that have sensors and actuators hanging off of them in an application. We'll then subsequently resurface our surveys, deploy those surveys, and have an exercise called clustering, where we will look at issues that you collect from cohorts of students on campus with the idea of constructing a persona. And so now this is where we pivot to the internet part of Internet of Things as we increase in sophistication the types of things we're doing in our applications. But before we begin, some administrative bits. So the reading by next week, which if my, yes, 22nd of March, keep forgetting it's March, please look at the Wi-Fi NINA documentation. That's the Wi-Fi programming library set of APIs for building network applications for the library, networking library, supported by the Arduino Uno Wi-Fi revision 3. And please do that with an eye towards looking at the networking examples. Today, I'll actually have a demo, a dangerous thing, a live demo, to show you some of the uses of these APIs. Project 5, which I haven't finished writing, I will write that and post that this evening, will be for a network sensor, and it'll make use of some of the things that we'll be talking about today. Now, of course, if you're using the campus network, you might have issues, and I'll talk a little bit more about some of those possible issues in the subsequent slides. I am catching up on the grading. You should have seen 4 pieces of graded material returned back. I do read every single thing that you write, and there were some points and questions that I directly addressed in the feedback section. I don't know what the student view of the interface looks like, but I do leave notes and messages for people. And so some of the general questions concern things about how I use certain items, particularly the teaming and the reflection part. As I said at the beginning of the semester, this course is sort of an experiment as it has never been taught before. And there are certain things that I try to assess. For one, with the teaming and the reflection, how things are going, right? That's feedback to see how the course is going for the students, if there are struggles, and also to address any issues that need my intervention, right? So when you're working in a group dynamic still comes into play, and sometimes there are pinch points where the group dynamic is not always very efficient. And that's something that I address with the group or with individuals from the group. And so those two things, teaming also is purpose with trying to ensure that all of the team members are contributing. Now, the contribution might vary from one project to the next, depending on the division of labor and other circumstances. But what I also try to assess is if there's a situation, and thankfully there hasn't been, where a team member is not doing anything, right? That is unfair to your teammates and also unfair to yourself. And so everyone's doing quite well, so congratulate yourself. I'm very proud of your efforts. This is a course that will involve turbulence ahead because there's no precedent for teaching it. And the first time you teach something, whether you knew it or not, you learn a lot about how to teach the particular course, as well as the confines of the infrastructure like network and other things available at the university. And so I do read every single thing you write, And there were some instances where people had some examples of things that I thought were pretty creative. And I said, wow, that's pretty creative. And so this is very much a thought course, but I do read everything, right? So please know that I do that, and I take what you write very seriously and take that to heart, as well as looking at how things are going. Okay. Any questions? No questions? No? All right. So please watch out. I will certainly post on the Moodle channel for the class when project number 5 is there. And you might have issues depending on how you access it. If you're using your own home network, everything will be hunky-dory, everything will be great. But if you're using some combination of the campus network, things might not go so well. I've tested it from Clark Wi-Fi network, but I'm not sure what would happen in the dormitories, the libraries. And if you're off campus and Clark-owned housing, I'm not sure what the network architecture is. So there will be some turbulence ahead, and I ask that you reach out to me, and we can always find a workable solution. Okay? All right. So let's see. To jar your memory, and it has seemed like we haven't met for quite a long time. It's been a week. And this is to jar your memory with some pieces of information that are going to be important to the demo that I'll be showing you. And so we talked about the process architecture for so-called network applications. And this is tuned to jarring your memory for using the Arduino ultimately as a server. And the demo I'll show you will treat the Arduino as a simple web server and to use URL suffixes, and I'll talk about that a little bit later, to control the board. In this simple example that I'll show you towards the end of class, it'll be to light up the LED and turn off the LED that's on the board. And so we said there are 2 roles in a so-called client-server architecture. We said there's an initiator, the client, and there's a responder, the server. And with this, in any network architecture, the example I showed you was in Python, but that was illustrative, and we will see the difference in a much more primitive implementation of sockets on the Arduino platform. And just to keep in mind that the Arduino is a microcontroller, right? It's not a full-blown computer, and it is much more limited in its resources, so they take certain liberties that you would never do on a general, or never implement on a general purpose computer. And so we said the socket is that construct, and it could be an object, as it would be in object-oriented languages, or it could be a set of APIs in procedural languages. And the socket construct is this mechanism that you use to send data out to the network or to receive data inbound from the network. And this, something is going on here. We also talked about the HTTP request and response message. And this is relevant to the demo because we're treating the Arduino like a web server. And so it's going to traffic in HTTP requests and HTTP responses. Now, the HTTP protocol is pretty important because it's the underlying protocol for applications on the web. But there are a lot of other applications, particularly representation state transfer software or service-oriented architecture, or RESTful SOA, that builds upon HTTP. Moreover, if you were to run Wireshark, you'd see a lot of HTTP type requests being generated by a printer, right? And a lot of these printer discovery protocols piggyback on top of HTTP. So the reason why many networking courses cover HTTP, because very many applications make use of HTTP as the way of sending messages, requests and response back and forth between the client and the server. They tag things on to this HTTP request. Then we talked about the HTTP response. It's what the server sends back to the requesting client. And this could just be, in the simple case, an OK message. I was able to do what you asked me, or it could be the contents of a file. Any questions about this? No questions? No? All right. And so we talked about 2 different types of services, the connectionless service, UDP, and the connection-oriented service, TCP. In the example today and demo, I'll show you TCP because that's what web-based communication is based on. Now, certainly we're not limited to HTTP when we implement services on the Arduino. You can use UDP, you can use TCP, you can piggyback on HTTP, or you could just send back and forth raw data between your client and your server. And so this idea of multiplexing or sharing the singular network connection, your interface card, is what the transport layer is purposed with. And we saw the contrast between the connectionless service, UDP, and the connection-oriented service, TCP, and that difference was in requiring the stamping of every datagram that you're going to send with the server's identity, its host name or IP address, as well as the port number. For TCP, we saw that you don't need any of this. Once you establish the connection, underlying this connection socket between the client and the server is this four tuple, namely the source and destination IP address and the source and destination port numbers. Any questions about this? No? No questions. All right. And so this figure we went over as an example of the so-called connection-oriented service, and you'll notice the difference between this figure and the figure before. In this figure for connection-oriented multiplexing as engendered by TCP, you'll notice these edges are bidirectional. And so once you create this connection socket between the client and the server, you can use that same portal or that magic doorway, if you want to call it that, for both sending and receiving data. Whereas with the UDP case, each one of these unique sockets is intended for a certain direction for your communication. Any questions? No? Jar your memory? All right. And so we also talked about addressing. And these addresses are meaningful to the network layer, so-called IP, Internet Protocol address. And these are globally unique, and they're used by routers to decide out which interface it should forward a datagram when it arrives. We said routers store and forward these datagrams, and it's the cumulative storing and forwarding from one network to another network, which results in your message going from one endpoint on one side of the internet to another endpoint on the other side of the internet. And so this address, so-called Internet Protocol address, in IP version 4, it's a 32-bit number, and it's written 8 bits at a time. And these 8 bits are typically cast in base 10 because it's easier for us to read. And so in this example, we have a bunch of networks, specifically 3 networks. Here's our first network to the left, your left, the second network to your right, and the third network down below. And one of the observations is that if you were to disconnect this router, all of the machines that are on these different so-called networks can directly communicate with one another. But if you want to go from one network, say this network on the left, and send a datagram to this network on the right, if there's no router storing and forwarding those datagrams, they will not reach their destination. And so these are so-called subnets. And a subnet has a rigorous definition. It's a directly connected set of devices that can send messages to one another without the intervention of a router stored and forwarding. And so this network could be wired, so-called guided media, things like twisted pair copper wire or fiber optic, or it could be unguided, which is the airways, your radio frequency broadcast for your wireless networks. And so the so-called subnet is how you identify a particular network, and the subnet part represents the high order of this 32-bit number. And so stylized schema, you'll see that this is the 223.1.1 network, the 223.1.2 network, and the 223.1.3 network. And the remaining low order bits of this IP address is the host number. And so with the subnet, we identify which particular network are you trying to reach. And then with the low order part, the host part, which host on that network are you trying to identify? Okay, any questions about this? Jar your memory? Yeah? All right. Okay. And so in the earlier days of networking, there were 4 different classes or categories of network, a so-called class A, B, C, and D network. And this A, B, C, and D network partitioned up the address space, the possible set of IP addresses, into networks that had differing number of hosts. And so a so-called class A network was the biggest type of network, and A represented the first decimal number, that position, and that gave you a network we could have up to 2 to the 24 many hosts. And what happened is that which they didn't envision when the internet was being developed, still is being developed, they didn't envision that there would be so many hosts attached to networks. So what ended up happening is that they ran out of unique IP addresses because they were giving out these subnets to various organizations. And so to make things much more flexible and also to help facilitate this idea of hierarchical routing, they implemented this notion of a subnet mask. And with that subnet mask, you're not dividing your network into class A, B, C, and D, but you specify this number here, the subnet, that represents how many bits for those upper level bits are used to represent your network or your subnet. Okay, any questions? No, no questions. All right. So then we also talked about the MAC address. And the MAC address is sometimes called a LAN address. And this MAC address is purposed with uniquely identifying your network card on your network. Now I stress on your network because this MAC address has to be unique locally, but it doesn't have to be unique globally. So if I'm in Germany on some network and you're here in Worcester on some network, we can have identical MAC addresses because we're on entirely different subnets. But the problem arises by some sort of happenstance if we're both on the same network with the same MAC address. And so that MAC address is used to identify which host or network interface card to which a frame is going to be directed. And that's for local network communication. And so we stitch together all of these local communications ultimately between a host on a subnet and its local router, since the router shares an interface with each subnet to which it's connected. And it uses that MAC address to send the frame to one another. And then ultimately, once you get it to the router, it stores, analyzes the IP address, and then forwards it using MAC address that it has for another subnet. Any questions? No questions? No? All very quiet. Not used to being back. Would rather be on spring break again. Me too. All right. And so in this example, we have a router, and you'll notice this router shares a MAC address with this network on the right, the left, I mean, your left, and it shares a MAC address with this network or devices on this other subnet on your right. And so we take our datagram, we initiate the send from, say, host A to its one hop or local router. This local router is often called a default gateway, and that's the first router that you send your frames to when you're trying to get datagrams off of your network to another network. Okay, and so once you get your datagram to the router, your router then analyzes the IP address, and it has a lookup table which it uses to determine for certain subnets, it's going to send that datagram out a certain interface. And then we talked about this idea of a switch. And a switch is a layer 2 link layer device. So you use it for connecting together hosts into a single network. And it implements what back in the old days, they used to call a hub and spoke architecture or network topology. And so with this, in the early days, you had your hosts on twisted pair copper wire or coaxial cable. They were physically on the same conductor. And one of the problems with this we discussed is that if you have two pairs of hosts, let's say host with MAC address A wants to send to A prime, and at the same time host with MAC address B wants to send to host B prime. Now, if they're sending at the same time, that means they're both putting signal energy on the wire at the same time, and you're mixing those sinusoids together. And so your 1 bits don't turn out like 1 bits and your 0 bits don't turn out like 0 bits. You're going to get corruption. And so that corruption due to two simultaneous communications is called a collision. And whenever you get a collision, Well, you have to decide which communicating pair is going to have access to the channel at a particular time. And we won't talk about those protocols. I'd suggest you take the computer network if you want to talk about collision detection, avoidance, and all that good stuff. But nonetheless, that collision results in degraded performance on the end-to-end send rate of bits on the wire. Because if somebody collides, you're not sending. And then if you're deciding who's going to communicate, you're not sending. And so the aggregate of all of that waiting and deciding is that you don't have full use of bandwidth because you're spending time waiting and calculating things instead of sending data down the wire. And so that being the case, this collision, as you scale up the number of hosts connected on your network, the collisions increase, and that further exacerbates the problem of degraded bandwidth over time. And so what this switch device did is it allowed multiple simultaneous end-to-end communications, or so-called collision-free communication. And what this switch does, it's kind of like a poor router, right? It does storing and forwarding, but it does it at the link layer using the MAC address. Now, this switch is completely invisible to all of the devices that are connected. They don't know the switch is there. They just think that they have a direct pathway collision-free on the link. And because this pathway is collision-free, you get a lot higher performance. And so sometimes for wired communication, at least on Ethernet, which is a link layer protocol, the predominant link layer protocol, you hear the term switched Ethernet. That switched part in the name switched Ethernet refers to these switch devices. And so right now, it's pretty typical to buy 1 gigabit per second switched Ethernet. That's very commonplace, and people are starting to pivot to 10 gigabit. And that's all because of this switch device. Any questions? No? All right, it's getting a lot faster. And so how the switch works is something called selective filtering. And it's kind of clever how they did it. It's very lightweight and it operates at line speed. And for many switches, this is implemented in firmware, right? This is not a software process that analyzes it because software is slow. Hardware runs at full line speed. And so you start out with the observation that if you have a frame that originates on a particular spoke in this hub and spoke topology, well, when it arrives to the switch device, that switch says, hey, wait a minute, the source was this particular MAC address. So subsequently, if I want to reach that MAC address or the host with that MAC address, I'm going to send it out that link from which it originated. And so it uses that idea to populate the so-called switch table. And then whenever it gets a frame, it looks up in its switch table and says, do I know where to send this particular frame if the destination is a certain MAC address? And so we saw an illustration of this. And in this example for the self-learning or populating of the switch table, the example is we have host with MAC address A that wants to send a frame on the same network to host with MAC address A prime. A could be a host, A prime could be the MAC address, for example, for its default gateway, for its one-hop router. And so A sends a frame, and the source MAC address is A, the destination MAC address is A prime. It sends it down its spoke, it hits the switch says, aha, I just received inbound this frame, and the source MAC address was A. So it writes down in this table, since it originated from A and it arrived in interface 1, I'm going to write down that if anyone wants to reach A as a destination, since it originated on interface 1, I'm going to forward it through interface 1. And so this table also has this so-called time to live field, and that's used to do garbage collection, to clean up the status of the table. This populating of the switch table, it's plug and play. You don't have to do anything. You just plug in your device and it just works. And that's because of this time to live field. It'll clean up these table entries. And you have to clean up these table entries because storage space is finite. Any questions about this? Does that make sense? Yeah? All right. Anyone want coffee? No? Okay. So now, when this frame arrives at the switch, it writes down this information in its forwarding table. Now it looks to say, okay, where am I going to send this thing? Out what interface? Because I have this destination MAC address A prime. it doesn't have an entry in the table. So what does it do? It floods. It sends a copy of every single interface except for the interface that it arrived on, because that doesn't make sense. Why would you send it back where it came from? And so we flood. And when each of the hosts, C prime, B prime, A prime, C, and B, get a copy of that frame, they say, wait a minute, this destination MAC address doesn't match mine. So that is not a frame for me. But lo and behold, A prime, or the host with MAC address A prime, gets a copy of that frame and says, wait a minute, that's my MAC address. This message is for me. It inputs into memory and it receives that frame, unpacks the datagram, and then forwards it up to the transport layer and ultimately to the application. Now, of course, this distributed systems principle called gossip, if two things communicate, they're going to communicate in the future. If this is a client A trying to make a request to server A prime, at some point A prime is going to communicate back to A. So let's imagine then this were, for example, an HTTP server, and you have the reply from the server coming back into the client. So at some point, A prime is going to initiate a frame, and A prime is going to send it along its scope. But for that frame, the source MAC address is A prime, and the destination MAC address is A. And so it hits the switch, and the switch says, okay, well, I just received this frame from source MAC address A prime. I don't have an entry for that, and it came or arrived as input on port number 4. So it goes ahead and it writes an entry in the forwarding table, A prime. I use interface 4 if I'm going to reach it with a time to live for the garbage collection. So now it says, okay, well, this thing, the destination is MAC address A. I look up the table, lo and behold, I have an entry, and it says forward it out interface 1. So it goes ahead and it does that forwarding. And so the cost here in the beginning is this writing down of the entry in the forwarding table and the flooding, but that only happens on the first communication between the two endpoints in each direction. Subsequently, it's just a forward based on a lookup from that table at full line speed. That's why it's more efficient. You pay the cost up front, but over time, the benefit is collision-free communication. Any questions about this? Does that make sense? And so when you go into some place like Best Buy and you pay between $100 and $300, depending on the bells and whistles, for this thing you call a router, it's not just a router, it's a switch. It's a switch, it's a router, and it's a bunch of other things. You can certainly buy a switch for individual use very cheaply, about $20 these days, a 4-port switch, 6-port switch. Okay, any questions? No? No questions? Okay, all right. So let's look at connectivity of your Arduino Wi-Fi revision 4, or revision 2 rather, I'm thinking of something else, to the Clark network. Now, I don't know what your housing situation, some of you live in the dorms, some of you live in private off-campus housing, some of you might live in, as I'm understanding, Clark-owned housing, some of you commute from, I don't know what your living situation is. And so this pertains to Clark's network, and it's the so-called gadget network that we're using. Now, as I understand it, the gadget network was intended for all sorts of devices students might have in their dorm rooms ultimately, or on campus. Game controllers that are wireless, smart devices like smart speakers and things like that. And so we started out with this general diagram of the internet. And Clark's network is a so-called institutional network. They have really wide pipes that are relatively high bandwidth from internet service providers. And so if we were to kind of blow up Clark's network, now I'm going to kind of wave my hands and make a big caveat. I don't know what the network architecture is for Clark's network, right? This is intended to be representative of the types of things that people do on institutional networks. At some point, some faculty want to meet with ITS to talk about what the network architecture is, with an idea of certain changes to support research, but that's conversation for another time. But nonetheless, we have our incoming link from a service provider. And many institutions the size of Clark often have more than one service provider to have redundancy, right? You don't want something to happen to that link. Maybe someone's doing construction or something like that, and a line gets cut. You don't want to lose all of your network connectivity, because for an information-based organization like a university, that's very catastrophic to lose your data connection. So you typically have a set of redundant incoming pipes or connections from an ISP, and these are very high bandwidth. They're typically at least gigabit, but who knows what Clark's is. And you also have other access into the network by virtual private network, and Clark does have VPN. And what this VPN allows you to do is to be outside of Clark's network. So this is the case where, for example, you were renting an apartment off campus or you're at home, how you can access those network devices that are on Clark's network, even though you're outside of Clark's network. Now, as you can imagine, you could certainly make these devices accessible, but that presents a huge security risk, because the moment you compromise one device, you can now use that as the platform from which you can launch exploits for other places on the network. And so the network, called the gadget network, as we talked about, a network is a set of directly connected devices that can send data to one another without the intervention of a router. Now, for an organization like Clark, these networks are virtualized. And so these switches have a lot of other features involved, where you can take all of the devices that are physically plugged into that network and treat them as if they were on separate switches, on separate networks. And moreover, you can chain these enterprise switches together, and you can have a name, for example, gadget, which exists in this building, in that dormitory, in that building, and it behaves as if you have a single switch that all these devices are connected to. And so those enterprise features, this ability to have virtual aggregations of things on network, creates these islands of connectivity. And the reason why they do this is because they want to shape the traffic and also protect against certain exploits that people might try to engage in. Now, a university, you might wonder, who would ever want to launch an exploit at a university? Well, it's a perfect environment to harvest people's credentials, people's financial information. Also, it's a perfect environment with which to launch attacks from someplace else. From who better than to try to bring down Amazon.com than to compromise 100 different universities and then have thousands upon thousands of clients send traffic to Amazon in attempts to bring down their servers. Okay, and so with this VPN, you authenticate yourself using software that you download and install off of Clark's network. And the one Clark uses is called Global Protect. And this Global Protect connects to a specific host, the VPN gateway that exists on Clark's network. Once you authenticate yourself to the VPN, you're now sending your data encrypted to the VPN, and the VPN proxies on your behalf all of the connections that you issue to assets that are on different networks or subnets on Clark's infrastructure. And so the Clark partitions Clark Wi-Fi, which is one network that you access, the guest Wi-Fi, which is another virtual network. There's Gadget, which is another virtual network. And these other two, these are assumptions. I'm pretty confident that they separate the operations, things like finance, financial aid, those sort of business operations types of functions. You don't want that traffic mixing with the rest of the network because it has other sensitive information associated with it. And so many organizations, they might partition, for example, all the wireless traffic being fed by some parts of your route infrastructure, all the wired traffic being fed by other parts of the infrastructure. And then oftentimes they divide these virtual networks based on purpose, like classroom versus administration and things like that. Any questions about this? All right, and so how do you get on Clark Gadget? My asking you for the MAC address was purpose with registering all of your Arduinos on the gadget network. Now, through arrangement with ITS, you're going to get static IP addresses, because if you're going to treat these Arduino devices with sensors and actuators hanging off of them, if you're going to treat them as servers, part of the prerequisite for being a server in the client-server architecture is that you have to have a static IP address. Why? Because if you're going to contact it, it has to be there continually. And so you go to this address to register your device, which I've done for each of you. And two of the things that you give it is, of course, the MAC address for your device, and that's the MAC address for my Arduino. And then you give it a name. The agreement with ITS was that you have to have in the naming schema for your device name, you have to have the course number. So I've done that for each of the MAC addresses that you've given me. Okay. And so once you do that, it gives you a password. And this password becomes your device password. You don't have control over it. It's generated for you. And you use this password programmatically on the Arduino to log in your gadget to the device network. Now, of course, if you were doing, like a printer or a smart speaker or something like that, you would enter in this password in the network information for your device. And so I've redacted mine because I'm not going to show you mine, but you get this screen, and this is the information that I sent to each of you in a point-to-point message on Slack. So if you haven't looked at your point-to-point messages on Slack, please do so and record this information. Once you register it in this interface, it goes away, right? So it's really important you capture it. I've captured it for each of yours. Now, the naming scheme that I've adopted was to have your first initial and your last name followed by the course number and the word Arduino, because we'll be doing this again for the Raspberry Pi in about 3 more weeks. Okay. Any questions? Yes. Whatever I was given, those were the ones that I registered. And in one case, I was given 2. One was from the class and one was a personal one. So the one for the class, I put a C Arduino standing for class Arduino versus Arduino's personal one. Thank you for asking. Any other questions? No, all right. And so these are all of the gadgets for this class. And we will be adding the Raspberry Pis at some point in the future shortly. So please make sure you get on right away when asked to send me your MAC address. There's a delay for doing this that I have no control over. It's dependent on ITS because they have other things to do than service this class. Okay. All right. Any questions? No? All right. And so coming soon will be to use the Arduino device as a server with the static IP address, and this is by arrangement with ITS. This allows you for off-campus use. So you could set up your Arduino, have it sitting in a classroom or somewhere. Someone else could use VPN to gain access to it through a browser or through a client program that you've written. So to do so, off campus, you have to have the VPN client software installed. You'd go to vpn.clarku.edu. It has a download for each of the major operating system platforms. You download it, install it, and then you start your VPN client. And now you can connect to items on the Clark network that you otherwise would not be able to. Okay, any questions? So this is what's coming soon. They're still working on the static IP address, but right now, and I've tested it yesterday and the day before and during break, you can connect your Arduino to the network on the gadget network and print out the IP address that it's assigned. And you can also then take this IP address and access it, right? The static part is still not up yet. Okay, all right, any questions? No, does that make sense? No questions? All right, and so let's look at some of the APIs. And again, the Arduino is a microcontroller, and it does things or implements certain aspects of the socket interface, the sending, receiving, and so forth, in a way that's a little bit different from what you'd see in a general purpose operating system. And again, the reason for that is because it's very limited in resources, right? And I'll point out where that is different. So let's start with the server APIs. Now, of course, the first thing you want to do, and this first one isn't necessarily a server API, it's a Wi-Fi API, you need to join the network, right? And so to join the network, you need two pieces of information for this API called Wi-Fi.begin. You need your service set identifier, SSID, that's the network name, and that's Clark Gadget with capital C and capital G. And then you also need the password. Now this password, that's the credential that was generated for you when I registered your MAC address. And so it's not going to be your regular Clark login password. It's uniquely this password for your device, which was generated for you. And so that's going to be programmatic, and that allows you to connect to Wi-Fi. But like your host, when you connect the machine to Wi-Fi, sometimes it might not connect. You have to give it time to connect, or you might need multiple tries to connect, depending on what the noise environment is like, all sorts of other issues. So once you connect, you'll get a status code from Wi-Fi begin, and the status code, I can't remember what it is, I'll show you in the code, tells you that it's successfully connected. Then, and only then, you'll know that you're connected physically to the network. So the next thing is we need to start the server. And we said a server is really just a process that responds to incoming requests, and it's always on, and it's associated with a socket. And we have two sockets. We talked about the so-called server socket and the so-called connection socket. Now, the server socket is associated with a port number, and that's how your TCP runtime knows to which process incoming data should be forwarded, or from which process outbound data has originated. And so when you create an instance of a server, you're creating a server socket with this Wi-Fi server. It's a class, and you're instantiating it, and you're giving a port number, in this case, port number 80. Now, because in the example, we're treating the Arduino like a web server, the well-defined port number for HTTP servers is port number 80. Okay? All right, any questions about this? No? No questions? All right. So underneath the covers, what happens? You create the server socket, and the server socket binds itself or associates itself with port number 80, right? And that lets the TCP runtime know, aha, port number 80 means it's going to this particular socket, the one that bound to port 80. So then once your server binds to a socket through the port number, or binds a socket to a port number, you need to start listening for incoming connections. Now, this listening for incoming connections means it's literally going to go to the network IO subsystem and wait for datagrams more specifically, to arrive. And so this next API, server.begin, assuming that you have a bound server socket, tells the runtime, start listening for incoming connections. So now you're sitting there waiting, you being the server process on the Arduino, you're waiting for incoming connections. But you have to tell it, go ahead and return a connection. And that's done by this next API, server.available, right? Now, in things like Python and Java, you'll see accept, right? And Arduino, they did it this way. Historically, why? I don't know. You'd have to look that up. Somebody knows. So when you call server.available on a bound server that's listening for incoming connections, it's going to return back another socket. Now, what it returns back underneath the covers is this Wi-Fi client. And what this server.available does, it gets the client connected to the server. And it's through that you use to get a connection to the client. It's just like our connection socket that we talked about in the Python example. Again, it's a microcontroller. They do things a little bit differently from what you would have in a general purpose operating system, something like Java or Python. So then when we want to send data from the server to the client, we can use server write, and server write is for arbitrary data. You can send a single byte with server.write with just your byte, your data, or you could send a set of bytes from a buffer. In that case, we have the version of server.write where you give it the buffer of bytes or an array of chars if you want to treat it that way, and also the size, which tells it how many bytes it's going to send from that buffer starting at the beginning. And so that's for arbitrary data. And so with your server, for example, let's say this was temperature server or humidity server. You have your sensors hanging off your Arduino. You create a server process. You then connect to it and give it a get message, and it sends back a byte of data. That byte might be number 1 means get me the temperature. Number 2 might mean get me the humidity. And it sends you back that information in the right floating point representation or integer if that's what you choose. Okay, any questions about this? That makes sense? And so because HTTP is so popular, the server has another set of APIs that is line-based. And the assumption here is it's text. And as I said, many protocols piggyback on HTTP. So it's a very useful pattern to send new line terminated text. And so this server API has this server.print line, which is how you send a line of text, and you can use character formatting as if you were printing out to the console. This last API call, a server.peek, says sometimes you want to examine what the next byte of data is going to the server without pulling it all out of the buffer that it's arriving on. You want to take a look at it because what that next character is or byte of data might determine something about your behavior going forward. And so server.peek does that. It returns the next byte incoming without advancing the so-called cursor. Cursor is a database term, which means where you are currently in the stream, right? And so when you read data from this coming into the server, you're taking that byte from the incoming buffer, and now it's no longer on the buffer, right? It's a stream of data, you're taking it off, and now at the head of the incoming buffer is that second piece of data that's arriving. Peek examines without removing. Any questions about this? Does that make sense? No? All right. So then let's look a little bit at the client APIs. You can implement your Arduino as a requester, an initiator of communication in a client-server architecture. Now you might ask, why would I ever want to do that? Now, at the beginning of the semester, we talked about an IoT system as being an interconnection of devices that engage in the sense, think, act cycle. So that means some devices might need information from other devices. And so in that case, one device would act like a client and the other device might act like a server. So suppose you have two Arduinos. One implements the LCD display and the other Arduino connected on the network has the temperature and humidity sensor. So in that case, you have the LCD display Arduino acting like the client. It connects to this server with the temperature and humidity sensor, and it says, what's the temperature and humidity? The response back is the temperature and humidity, and then the LCD display displays what it just got from the other Arduino. So what the real magic is, so to speak, is when you have this device-to-device communication, and that's what the client API is purposed with, implementing or allowing you to implement or facilitating your implementation of this requester role among devices. And that's where it gets really, really interesting. Now, certainly, I don't know if they've ever had a course on the books here in distributed systems, but distributed systems is the study of these interacting devices or interacting entities on the network. And there are all sorts of protocols and algorithms that present the illusion of a single system among a bunch of communicating parts scattered around the network. And so you can get a whole master's degree, which is what my master's was in, parallel and distributed systems, on all the interesting APIs and protocols and things you can do when devices and hosts and processes interact together on a network. Okay, so our client APIs, of course, you want to create a client. And you're going to create a client socket. Now, this assumes the connection-oriented service is different with connectionless. And Wi-Fi client.client on the client side creates your client socket. and you're going to need to initiate the connection. And so this second API, the second one, client.connect, that's how you tell the client to go ahead and start a conversation, establish the resources on the endpoint, start this conversation with the server. So you need two pieces of information. You need the server name, that could be a host name or an IP address, and you also need the port number. Port number 80 is for HTTP. So for example, when you type in www.clarku.edu or some website on your web browser as a convenience to you is supplying port 80 because it knows it needs to engage in the client responsibility for the HTTP protocol. And port 80 is the port you use to contact a web server or HTTP server. Okay, any questions about this? But programmatically, this is to allow you to implement the client. So one of the parameters to the function call is the port number. Okay. All right. Any questions about this? All right. And so to make things easier, one of the things the enterprise to do is to, not make it too much of a pain to send data from the client. And so this next API, client.println, you give it a string message with the usual type of formatting and different versions of it. And this is how a client, once you've connected to a server, how it sends a string message to the server. So you connect. Once the status code tells you you're connected, you then just use that client reference and do a print line, and it sends that data to the server. So with this print line, you can do all sorts of formatting to try to make your life much easier. Next, if your client can send data to the server, you should be able to read the response back from the server that arrives inbound to the client. So client.read does exactly that. And you can read two different versions, either a single byte of information, that's client.read, or you can read some number of bytes, which you have to target to a buffer. And so this next one, client.read, with two parameters, we have the buffer, where you're going to store the data it reads, and you have size, which is the number of bytes you're going to read. So for example, if you're reading both temperature and humidity, right, return back to the client, your buffer might be of size 2 bytes, and maybe you have the first byte is the temperature as an 8-bit number, and the second byte is humidity as an 8-bit number. Okay. Any questions about this? That make sense? Okay. And so then next, client.available. Now, whenever you're doing client-server communication, you need to know how much data has arrived. Now, the tricky part in general is that you're not always sure that all of the data is there that you need. So let's imagine you had a 32-bit representation for a number, while 32 bits is 4 bytes, right? And so you might decide, okay, I'm not going to fetch my response that I'm expecting to be 4 bytes until I know there are 4 bytes waiting in the incoming network buffer. And so this next API, client.available, will return to you a number, and this tells you the number of bytes that are reading. Because in C, C++ side of the world, data representation, you have to understand data representation to build up the quantities that you need. Okay. And you're also concerned about byte ordering and all sorts of stuff. And so it's not enough just to say, client, get that data that's coming in. You need to know ahead of time, because you wrote the application, how many bytes are coming in. And then you check, okay, do I have the 4 bytes back from the server yet that I'm expecting back? Okay. Are there any questions? Questions now? Does that make sense? All right. So let's go to the HTTP example, and live demos are one of the most dangerous things in computer science. So we'll see. It worked in my office. It worked yesterday, and watch it not work now. But anyways, so we'll give it a shot. So we're going to have the Arduino connect to Clark Gadget. I'm going to print out the IP address that it's assigned. Then I'm going to point my browser to that IP address and hit enter and do an HTTP GET. It's going to send an HTTP request to the Arduino server. It's going to parse out that response, and it's going to use that response, pull out a suffix on the end of the URL, and it's going to use that suffix to turn on the LED or turn off the LED that's built into the Wi-Fi revision 2. Now, one of the caveats about the Wi-Fi revision 2 is that when you use the built-in LED, everywhere in the documentation, you'll find that the built-in LED is on digital I/O pin 13, but it's different on the Wi-Fi revision 2, right? I think it's pin 25. So what you should use is that constant called LED underscore built-in, right? And that will map correctly when you set up your device. It'll map correctly to the right digital I/O pin that'll allow you to turn on and turn off the LED that's built in, okay? So please use LED built-in, and I've posted the INO file for the code alongside the slides for today. All right, so that's essentially what I'm gonna be doing. So let me pull that to the background, the slides, and I'm gonna pull up the IDE, and I'm gonna walk you through the code, but I'm not gonna download this because I don't want you to see my password, right? Anyways, so let's see if you can see that. Okay. All right, so here in the stub, the SSID is Clark Gadget, and the password is just your password. And for your own implementation, you're gonna use that password that was assigned to you by ITS, and I sent you that little snapshot that tells you what your password is for your device identified by the MAC address. And so we start out, we include spi.h, which is needed, and Wi-Fi Nina.h, which pulls in the definitions for the Wi-Fi Nina library for the Arduino. And just like we talked about with what we call the anatomy of a sketch, we have the includes up top, first 2 lines. Then we have a number of defines. Now, these defines, you'll notice here, LED underscore pin. In that define, I'm defining it as LED built-in, right? And again, number sign define is just the replacement. And it's this replacement, LED built-in, it goes to the pin number. It'll actually input an integer in place of that when it does the pre-processing step. Okay, so we also have the baud rate, and I defined something in this example called connection attempts because I didn't assume that the first time you're going to try to access the Wi-Fi is going to be successful. Now, if you have a lot of noise in the environment, or maybe it's very humid, you have a lot of moisture in the air, well, water is not a very good conductor of radio frequency energy, right? And so that could get in your way. And so I don't always assume that the first time you call Wi-Fi begin, that it's going to connect successfully, right? You want to make sure that you're trying a number of times with a pause between each of those tries. Now, I gave it 5,000 milliseconds, which is connect, retry, delay. You can season it to taste, right? If you're at home, it's always, for me, first time, right? Here, it might try, as of right before class, 2 or 3 times. It might even change in this room. I have no idea what's going to be in this room. Okay, so that being the case, we have our defines in that other section for our constants that are useful in our anatomy of a sketch. So then the next section, I define all of my data structures and my variables. So I have the SSID and the password that we talked about. Now the password I already pre-downloaded is the actual password that I have for this, so I'm not showing you that. And then we have the status, that's going to be the status of the radio that the Wi-Fi subsystem on the board uses. And that status is going to tell you whether or not your connection to the network was successful, because you can't proceed if you're physically not connected to the network. Okay. All right, sorry about that. Okay, so you always want to make sure you check the status when you connect to the network. So then attempts, that's just some bookkeeping to know which attempt of the number of attempts that I'm currently on. And then I have a data structure for the MAC address. I'm not going to talk about that because we've done that before. And then the IP address, because I'm going to use that to print out once it connects. And then here, LED state. This LED state allows me to record whether the LED is currently on or off. And I'll show you about that a little bit later. So we have our server. We create our server and we bind it to port 80. And then here, I'm initializing what's going to be the connection socket between the server and the client. If I didn't have this assigned and I just said semicolon, in C, C++, you need to initialize your variables, because if you don't, it'll just carve out some piece of memory and interpret what value happened to be in that memory before as if it were valid. So it's really important in C, C++ to initialize your variables in your data structures. Things like Python and Java, they're really nice because they do it for you, but C and C++, you need to do that yourself. Okay, so that's just an initialization of a reference that ultimately will hold the connection socket when an incoming request occurs. Now, one of the wonky things about the server APIs in Arduino is that when you send a response, it'll send that response to all of the connected clients. That's not how it works in a general purpose operating system. Once you get the connection and you send a response, it'll only send the response to that particular client that connected to you associated with that connection socket. So it's a little different. It assumes all the clients are going to get the same response. And so the assumption for our class will be that only a single client is connected to a single server and not multiple clients to a single server. When we use the Raspberry Pi, you'll notice that's entirely different. Raspberry Pi is an embedded computer and works more like a general purpose compute device, okay? All right, so that's something to pay attention to. So we have our setup and our loop entry points. In our setup, we have the usual start for serial begin, and it's kind of useful to print out useful information to the terminal for part of your debugging and understanding what the program is doing. And then in this while loop here, we are attempting to connect. And for each connection attempt, you'll notice here on line 50, I have Wi-Fi.begin. Each time I assign the result of that to status, and I check that status code to see if I'm actually connected. I increment my attempt because I want to know how many times I'm attempting before I just give up. Okay. All right. Any questions about this? No questions? All right. So then once I'm connected, I echo something to the terminal. I print it out through serial print line. And then if I am connected, I go ahead, just for good measure, and I print out the MAC address. Okay. Any questions? No? Oh. So now, at the end of the setup, I say go ahead and let the server start listening for incoming connections. You only need to do that once. Once you listen for incoming connections, each time you iterate in the loop entry point, you're saying go ahead and get the connection socket so I can talk to that particular client. Okay. So then from there, we do this print Wi-Fi status, and I'll show what that is. And we also, the last thing in setup, we set the LED pin to be output. And that's what we're going to use to light up the LED or to turn off the LED. And that was taken care of by the number sign defined to use LED built-in, which is another constant given by the Arduino APIs. Any questions? No questions? No? All right. So now let's look at this print Wi-Fi status. Now that's just a little bit of bookkeeping, didn't have to do that, but it's visually pleasing to kind of get information about your system. But for this particular demo, what we're interested in is the IP address that we're going to use to connect the browser to. And so here we get the local IP address, okay? And we go ahead and we print it out and we look at the signal strength. Now, one of the things that you're given when you connect is how much energy there is in the wireless radiation going between the access point and your device. And that's a logarithmic scale called decibels, right? And so the signal strength will tell you, I'm connected, but my signal isn't very strong, and that's going to result in having slower communication, okay? All right, so the part that is of most interest here is these last two function calls, the print line and printing of the IP address. So it's saying if you want to connect to this device, use http:// and the IP address. We're not using the host name, okay? All right, any questions? No questions? All right. And so this Print web is the routine. Let me go to the loop here. Loop entry point. So loop is fairly simple. First, we get the incoming connection, right? So this is to get the connection socket so that the server can talk to the client. So then I print out the LED state just for good measure, for debugging purposes. And if I do have a connection to the client, because it's not assumed that getting a connection socket is going to work, client might not be there, I go ahead and I call this print web. And based on what this print web does, which we'll talk about in a moment, I either set the LED high, turn it on, or set the LED low, turn it off. So this print web is purpose with taking the incoming client request, it's an HTTP request, and it displays the response, which is ultimately a web page, right? And that web page has two references, one for the same URL /h and the same URL followed by a /l, standing for high and low. So what happens is my browser will display an interface and it will have two links. I click on one link and that'll turn on the LED. I click on another link, it'll turn off the LED. And so here, if the client is connected, I go ahead and I read all the data from the client. Now, a bunch of different things can happen. Either I read and it's an empty request, or I read and it's a non-empty request. So here, when I read, recall that read is 1 byte at a time, or 1 character at a time. So I keep reading, adding on to the current line, which is a stream, until I get what I think is a command, okay? An HTTP GET request. So once I have that, well, okay, I go ahead and let me do this part first. I echo back or return an HTTP response back to the client, which is a very simple web page, and it has 2 pieces of text, 1 line that has an href or reference with a /h right here, and another line that has text and a reference that has a suffix of /l on it. And when you have an href in a web page, if you don't give the full URL, it'll assume the URL that you use to get this particular page. And so what that's doing is allowing you to click, and it causes the client to send another HTTP GET request with a URL suffix of capital H or capital L. And that capital H or capital L on a subsequent GET request is checked down here. It says, does the current GET request line end in /h or does it end in /l? If it ends in /h, it sets the LED state to true. If it ends in /l, it sets the LED state to false. Once we get down to the bottom here in the loop, given the LED state, it's going to go ahead and turn on the LED or turn off the LED. Okay, any questions about this? That makes sense? So let's actually see it and stop talking about it. We only have 4 minutes left. Okay, because I have to, because I'm recording and all that stuff. But let me go ahead and I'm going to plug in my Uno. And here's the Uno. I'm going to connect the serial monitor. And you'll notice, oh, where'd it go? Hello. No line ending. Not connected. Give that a shot. Sometimes you have to exit the IDE. Let me do this. Let me exit this and let me restart the IDE. Hence the danger of live demo. Hello. There we go. And the share, let me see if the share went away. Yeah, the share went away. Shift. Let me do that. Control there. Nuts. Control. IDE. Shift. There we go. Let me do that. Share. All right. So bring back Arduino. There we go. All right, here we are. So you'll notice here, it gave me the http://10.202.45.22. So I'm going to bring up my browser, and you see the browser here. 10, well, did it before my office. So let me hit enter. And when I hit enter, you'll notice you saw the GET request in the server printed out to the console, and LED state is 0. So now let me hold up my Arduino board in the camera, and let me go ahead, turn the LED on. And you'll notice that amber, or is it orange LED here is now on. If I click LED off, it turns off that LED, right? And so if we, oh, nuts, I forgot to run Wireshark. Yes. Yes, and it's supplying power. Yes, yes. This is only power. I could like have a battery or something that plugs into the wall, and you could connect to it. Once the static IP address part is up and going, that you won't even need to do this with the serial. But my reason for connecting it to the cable is for power, but also so I can see what the IP address is that I'm printing out. Any other questions? Okay. Well, if I unplug it, it's gonna, but I promise you it will work, but I still don't know what the IP address would be. And so I still need that serial terminal connection. And so that's where we are right now. But going forward at some point, when ITS finishes everything they need to do, you'll say for this MAC address, it's this static IP address. So you're guaranteed once it's running, it'll have that IP address. You could also have the LCD display attached to it and write out the IP address on the LCD display, but that's not something I want to add extra work to do. So I was going to run Wireshark. Let me run Wireshark, and I'll end with that. Let me go back, and I will go back to the original website. Hello. What just happened? It's not giving me my cursor. So let me do turn on, turn off, turn on, turn off. And let me go back to Wireshark. I'll stop the capture, HTTP. And you'll notice here, I did turn on, turn off, turn on, turn off. You see the HTTP GET request, and you'll notice GET/H. You see the response back to the client, said okay, and then the GET request /L, right? And so one of the things that you'll be doing is running Wireshark to debug what's going on and convincing yourself that this actually works. Okay, any questions? All right, so we are at 1:14. We end at 1:15. Let me just bring back the slides. And that is all I had for today. So I will see you all on Friday. Please look out for my announcement when the assignment is posted. Welcome back. And we'll end there.